In this next example, I'm at the beach. I throw a beach ball up in the air. And the question is, how hard should I throw that ball if I want the maximum height that the ball gets in the air to be 7 meters? In other words, if we're looking at the height function plotted against time, this function is measuring how high the ball gets in the air over the different range of time values. I want the apex, the top of that parabola, that's the highest point that the ball gets, I want that to be 7 in meters. Now, on its own, we can't actually answer this question. We're also given that the height is the following function. We're given the height function. It's minus 5t squared plus v naught t. That's just given to us in this problem. Now, what exactly is this v naught? Here, v naught, that's just some constant, and I claim that that constant actually represents the initial velocity of the beach ball. So I'm assuming that I'm standing on the ground so that the ball starts at a height of 0. You can see that because if you plug in h of 0, both of the t's will be 0. So h of 0 is 0 because we're on the ground. The ball starts on the ground. That corresponds to the fact that the ball starts on the ground. I guess I'm throwing it from the ground somehow. But initial velocity, that's different than the initial height. So remember, the velocity as a function of t is the derivative of the height function. And now if we go and look at this formula here, let's take the derivative. So we bring the 2 down, it multiplies by the minus 5 to give minus 10, and then we subtract 1 from that exponent, leaving just a t. For the next term, the derivative of just t on its own will be 1, so if we multiply that by the constant v naught, we'll just get v naught. So now remember, v naught doesn't depend on t, it's just some constant. And check it out, what is the initial velocity according to this formula? The initial velocity, that would be the speed, the derivative at time 0. That just means plug in t equals 0 into this function that we just found. But now the minus 10 times 0, that's just 0. So hey, it's exactly v naught. So this calculation, this is justifying why v naught is in fact the initial velocity, that constant. We read v sub 0 as v naught. Okay, great. What were we supposed to be doing? Right. What's the question asking? It's asking, how hard should I throw this ball if I want this max height to be 7 meters? How hard? That's asking us how fast must we throw it. In fact, it's asking us precisely to find this initial velocity that'll make the apex be a height of 7. So we need to solve for v naught to make the apex occur with a height of 7 meters. The idea is that to the left of the apex we have negative velocity, to the left of the apex we have positive velocity because we're moving upward. Let me write that down. So in this range of t values, the velocity is positive because we're moving upwards. But to the right of the apex, the velocity is negative because we're moving downwards. the ball is falling. And then the apex then corresponds exactly to when the velocity is equal to 0. That's the key to finding the apex. It's when the velocity is 0. So let's take our velocity function. That's h prime of t. That depends on this constant v0 that we want to solve for, which is really good, because then when we set that equal to 0, setting the velocity equal to 0, that's exactly happening at the apex of the curve. That occurs at the apex. That happens when the ball turns around, when it starts to fall. And this is fantastic because this is an equation that we can actually solve. And you might say, hey, I'm going to solve for v0, and that's cool. You could solve for v0, but actually I want to solve for t in terms of v0. This is going to be a multi-step process. Let's first solve for t. If you move the minus 10t to the right-hand side, you'll get that v0 is equal to 10t. And so, what's t itself? It's just v0 divided by 10. That doesn't solve the problem yet, but in the next step it will, because this is the time value at the apex. This is the t value when the ball turns around. That's when the ball is at a maximum height. Okay, why do I care about that? Well, let's plug it in not to the velocity now, but to the original height function. I'm going to plug in that special t value, the max height t value, into the original function. Remember, the function here is minus 5t squared plus v0 t. So I'm going to plug in v0 over t into that function. We get minus 5 v0 over 10 squared plus v0 times t. T is v0 over 10. Very good. What is that? That's the height at the apex. Because this is the height function. This is the height at the apex. And remember, in the problem, we want that to be 7. So we're just going to set this output of the function equal to 7. Trying to force the max height to be 7. So this looks complicated, but when the dust settles, it won't be so bad. Let's do the algebra. Now we're trying to solve for v0 squared here. How are we going to do it? Well, so the initial velocity that we want, this was the whole point of the problem, to solve for the initial velocity that'll give us a height of 7 meters, it's exactly the square root of 140. Now, what is the square root of 140? Well, if you plug it into a calculator, you'll get about 11.832 or so meters per second. That's the answer. That value of v0 is the speed at which we should throw the beach ball to make its maximum height be 7 meters at the top of its path. It's time to talk about the second derivative. What does that mean? It just means take the derivative a second time. So what do I mean by that? Well, if we have some function f of x, then we have this process of taking the derivative. We can use this other notation d by dx just to stand for the operator, which means take a function and then spit out its derivative. Take the derivative of that function. So if we take the derivative once, we get the derivative function. Remember, that's given as the limit of the slope of the secant lines, or in other words, as the limit of f of x plus h minus f of x over h as h goes to 0. That was just our definition of the derivative. And now what I'm saying is, hey, we can just do that again. Let's just take the derivative of f prime. So you can think of this being the same process, but starting from f prime. We write that as f double prime, f prime prime. That is the second derivative. By definition, it's the derivative of the first derivative. So you just use the definition of the derivative, but with primes everywhere for your f. So this new function is the second derivative of the original function f. We say second because there's two primes there. We've taken the derivative twice. All right, and now you can actually keep on doing this process forever if your function is well behaved enough. You could take the derivative again and get three primes. I won't write down the formula. It would be the same sort of thing. This would be the third derivative, and so on. You can just keep on doing this process. Okay, so let's see this in action. What am I talking about? Let's see, let's suppose that f of x is the function x to the fourth plus 3x squared. Nice polynomial function. Let's take the derivative once, the first derivative, as a function of x. So using our basic rules, when we're taking the derivatives of polynomials, we just take the exponent down and reduce by 1. So the derivative of x to the fourth is 4x cubed. The derivative splits apart over sums, so then we can just add on the derivative of the second piece. The 2 needs to come down and multiply by the 3 to give 6, but then we subtract 1 from the exponent and we get 6x. So that's the first derivative. And now, what would the second derivative be? Remember, that just means take the derivative of the first derivative. So we just take this new function we got and take the derivative again. The 3 will come down, multiply by the 4 to give 12, and then we subtract 1 from the exponent, so we get x squared. And then we take the derivative of 6x. That's just the constant 6 out front. So this, under this terminology, we might call this the first derivative to distinguish it from the second derivative. And if we wanted to, we could keep on going. The third derivative would be 24x, because the 6 would disappear. The fifth derivative would be 24, and then finally the sixth derivative would be 0, etc. Okay. Now, why in the world do we care? Why is this a reasonable thing to do? Am I just taking derivatives willy-nilly for no purpose? Well, I think it's best to think about the relationship between position and velocity in order to understand the second derivative. In general, the second derivative measures the rate of change of the rate of change. Sort of a mysterious statement, but it is true. The second derivative measures the rate of change of the rate of change. And that might not make much sense the way that I've said it, but you're actually familiar with this idea. This is precisely the idea of acceleration. So, suppose that p of t is a position function. So this is giving us the position of an object at time t. Then, as we've seen, the first derivative is giving us the rate of change of position, how much the position is changing per unit time. Well, that's the velocity of the object as a function, the velocity function. The velocity of the object at time t. And now, what happens if we take the derivative again to get the second derivative? Well, that's measuring how much the velocity is changing, right? And think about it. If you're driving in your car, you're going 40 miles an hour, and you want to go from 40 miles an hour to 60 miles per hour, you got to step on the accelerator. You have to accelerate. So to change velocity, you accelerate. The change in velocity is called acceleration. So the double derivative, the derivative of the derivative, is the acceleration, which means the instantaneous rate of change of velocity. And again, this is a function of t. We can evaluate it at different times to find the acceleration at those different times. So this is a really beautiful hierarchy of concepts. As we take derivatives, we go from position to velocity to acceleration.
Tibet.
Let's see these ideas in action. In the next example, I throw a piano off of a cliff. The height of the piano above the valley floor is given by this function here. It's p of t equals minus 16 squared plus 20t plus 50. And now that height, we're going to measure it in feet, and that function gives us the height at time t measured in seconds. Now, let's just analyze this function for a bit. First of all, what does it mean if we plug in t equals 0? That's the initial position. If I plug in 0 for t into the function, these first two terms are both 0, and so we end up with 50 feet. That is the initial position of the piano. That's the initial height. And we can see that that number in the original function. It's that constant term. So that constant term 50, that's telling us the initial position. It's common to abbreviate the initial position to p naught. That's a p sub 0. You often see that. It's sort of shorthand for p of 0. So in our little picture here, we might illustrate by saying that this initial height is 50 feet. Okay, great. So far, so good. Now, let's understand the velocity. The velocity as a function, we might write it as v of t, v standing for velocity. It is precisely the derivative, the first derivative of the position function. So let's take the derivative of this polynomial with respect to t. Well, starting with the first piece, minus 16t squared, if we take the derivative of that, the 2 comes down and multiplies by the 16 to give minus 32, and then we subtract 1 from the exponent, so we have minus 32. Next up, we take the derivative of 20t, and that's just the constant 20. And now the plus 50, that's a constant function, if you're just looking at 50, so its derivative is 0. Great, so that's the velocity function. What does p prime of 0 represent? That's the initial velocity. So we can figure that out, the initial velocity of the piano, by plugging in t equals 0. And we find that the initial velocity is 20. That's 20 feet per second. So this is the initial velocity. We might abbreviate that to V naught. This is saying that we're throwing the piano upward at a rate of 20 feet per second at the beginning of the process. Going back to the original function, we see that that constant 20 also shows up in the formula. That coefficient in front of t is our v naught, our initial velocity. Okay, finally, let's find the acceleration of the piano as a function of time. Acceleration, you might call it a of t, a for acceleration. It is the rate of change of the rate of change of position. It's the second derivative of the position function. Well, we already know the first derivative, it's minus 32t plus 20, so we just need to take the derivative of that. Minus 32t, the derivative is minus 32, plus 20, the derivative of that constant term is 0. So we see here that the acceleration is constant at minus 32. And now the units here are feet per second squared. That's because it's a rate of change of a rate of change. There's 2 time units for the same reason that area has 2 length units. So meters squared is how we measure area. Feet per second squared is how we measure acceleration. So we found that the acceleration, in this case, the acceleration is due to gravity pulling downward on the piano. That's what's changing its velocity, is constant at minus 32 feet per second squared. How do I know that's due to gravity? Well, think about it. If I threw the piano up and there were no gravity, it would just continue on at the same velocity, that same initial velocity of 20 feet per second, off into the air and up into the atmosphere, and it would float away forever, right? But that's not the case. Gravity is at play, and it pulls the piano back down. It changes the velocity. That's why the second derivative is the acceleration, because it's measuring the change in velocity. So we can graph these 3 functions next to each other and get a sense of how this is working. I'll just make little sketches of them. The first graph will be the position function. It starts at a height of 50 at the top of the cliff. The piano goes up, it reaches an apex, gravity pulls it back downwards, and it crashes to the valley floor. Next, what does the velocity function look like? The velocity function is minus 32t plus 20. So the velocity function starts at a height of 20. We're going to need the negative direction 2 here. And then it is a line. It's minus 32t plus 20. And so it's a line whose slope is minus 32. It roughly looks like that. And this point right here where the velocity is 0, as we've seen, that's going to correspond to the apex of the parabola. So here v equals 0, that exactly corresponds to the point at which the piano is at its maximum height. So v equals 0 happens at the apex of the parabola. Okay, and now finally, what's the acceleration function look like as a function of time? The acceleration function is just constant at minus 32. So here's minus 32. The acceleration is just constant, pulling it down at a rate of minus 32. So that value minus 32, that's the slope of the velocity function. And similarly, the values of the velocity function, it's the height of this line is the changing slope of the initial parabola. So we can see that in taking the derivative twice, we go from a parabola to a line to a constant, a horizontal line. And at each point, the values of a function are telling us the slope, the instantaneous rate of change of the function before. Now, going back to the formula for p of t, we observed that the initial velocity and position were there in the formula already. And now notice that this constant acceleration we found, minus 32, it's secretly in there as well. It's exactly twice this constant.